I'm going to introduce Hendrik de Snoo. That is from the University of Groningen, that is going to talk about the Lebesgue decompositions for linear relations, semi-bounded forms, and pairs of non-negative operators. Thank you very much, Henk, for joining us.
Okay, thank you. Well, good afternoon to you. I'm very happy to be able to speak in your seminar. It gives a possibility to renew old friendships. In one case, this goes back to over 34 years, 35 years, I think even. As the title of the talk indicates, I will report on joint work with Seppo Hassi. Some 20 years ago, when we were cooperating with Zoltan Sebastian and Franek Safranic, we became interested in these operator versions. And in the past few years, we became particularly interested in mutual singularity, mathematically speaking, of course, a notion which became a big influence. So I will start now with the lecture. I got the impression that Carsten Drunk has been talking in the seminar before. Maybe he talked about similar things, but if you don't mind, I will just do what I had in mind anyway. So here is the first slide. Everybody knows that for a pair of measures mu and nu, there exists a Lebesgue decomposition, mu1 and mu2. mu1 would be absolutely continuous with respect to nu, and mu2 singular with respect to nu. And on top of that, mu1 can be expressed in terms of mu via the radon-Nicodim derivative with respect to nu. So here are these gentlemen, Lebesgue, radon, and Nicodim. And now the point is that Lebesgue decompositions for measures also exist for linear operators and quadratic forms. And the point of the talk is that I would like to show that there are much more decompositions in this field, which we call Lebesgue type decompositions, and that there are radon-Nicodim derivatives corresponding to these decompositions. Maybe it is good to at least give some historical survey. The first one, as far as we know, who did this was Ando in 1976, and he considered pairs of positive operators. And then 2 years later, there was this Barry Simon who did it for quadratic forms. Then it took a couple of years before Jorgensen and Ota both considered similar decompositions for unbounded operators. And then still a little bit later, there were by Isomino decompositions of quotients of bounded operators with respect to closability, and Lebesgue type decompositions of positive operators. And our point is that actually all these things could be connected. You see, what Ando did was to give a Lebesgue decomposition, and he did not specify how many of such decompositions would exist, but at least he gave a uniqueness criterion for the Lebesgue decomposition. Simon gave Lebesgue decompositions for a single semi-bounded form, and he suggested the study of pairs of forms, which we did later with Sebastian. As I mentioned, Jorgensen and Ota gave similar decompositions for linear operators, and Isomino did more or less the same, but in terms of a special representation by means of pairs of operators. So the message here is that various compositions that we have discussed above can be obtained from the corresponding results for just linear operators or relations. In fact, one could do this for operators, but for the same amount of money when we can do this for relations, and it does not make any difference really. So in the present talk, what I would like to do is to give an overview of our recent work and the formal aspects, and mainly the analytical descriptions of the measure theoretic notions, I would leave aside as much as possible. So first I would like to discuss the decomposition of linear operators and relations. Then to discuss the decompositions of semi-bounded forms. And then as an application to look at Ando's decomposition of pairs of bounded non-negative operators. And then when there is time enough, then I will say a couple of words about the Rado-Nikodym derivatives for operator range relations in the setting of Ando as well. So the key object that we discuss is the set of linear relations between Hilbert space H and K, and we denote these by LHK. And so a linear relation is just a subspace, a linear subspace of the product space H times K. And the elements of this relation are denoted by F, G. And so then we have the well-known associated notions domain, range, kernel, and multivalue T. And the advantage of the relations is that one can talk about formal inverses by just flipping around the entries of the relation. And so then the domain of the inverse is the range of the thing itself, and the kernel of the inverse is the multivalued part of T. The multivalued part is the set of all these elements F, G, where the first element F is 0. And so if you see this, then it is clear that a linear relation is the graph of an operator if and only if the multivalued part of T is 0. For linear relations, as for sums, as for operators, we have sums, pointwise sums like T1 plus T2 as indicated. And you see directly from the definition that the multivalued part of the sum is nothing but the multivalued parts of the sum of the individual multivalued parts. Of course, the domain of the sum is the intersection of the domains. And we will be mainly interested in this talk in sums where the domains of the entries are the same. So you don't have to take intersections. Sometimes there is also a use for the so-called component-wise sums, where instead of the operator-wise sums, we now just add all the entries accordingly. And then I should mention that, of course, there is this definition of product of two relations. If you have two relations, T1 and T2, the product is as indicated. It consists of all the sets Fg, for which Fg prime is in T1 and G1 is in G. So these are just formal aspects. And then the thing that really is important is, of course, the notion of adjoint of a linear relation, which we do in a geometric way. We take the adjoint, it's just the orthogonal complement of the relation after we flip-flop, or we take the orthogonal complement and then we flip-flop. Flip-flop meaning phi psi goes into psi minus phi. And so if you do this, then you see that T star is as indicated. You just get all Fg for which GH is Fk for all pairs HK and T. And so you see it's actually that in the case of operators, this is precisely the definition of the usual adjoint. One thing that one should keep in mind all the time is that the adjoint T star is automatically linear and closed, being an orthogonal complement. And we can calculate the multivalued part of the adjoint by the orthogonal complement of the domain of T. So if we have a densely defined relation, the T has always an operator as adjoint. Now, this geometric definition of the adjoint is funny because we can also take the double adjoint of a relation. And as I indicated, you just use this flip-flop in the right way. And what you see is that, in fact, T adjoint adjoint is the orthogonal complement of the orthogonal complement of T. And so you have the closure of T. And it is a good idea to keep remembering that if we take adjoints of sums, we really have to be careful. The adjoints, the sum of the adjoint is contained in the adjoint of the sum, and likewise for the operator, for the product. And we only have, when we know that one of these entries is a bounded linear operator in the sum, or T2 is a bounded linear operator in the product, we have equality. Another thing is that we will talk about closability and singularity of linear relations. First of all, a linear relation or an operator is closable if we have these three different equivalent conditions. The multivalued part of the closure of T must be 0 and the other two. Clearly you see that 1 and 3 here are the same. This is clear. You see also that 3 implies 2. Because if 3 we have the domain of the closure of the domain of T star is all of K, then certainly 2 is true. But also 2 implies 1. Because you see that if the range of the closure is in this domain, then also the multivalued part of the closure is in this domain. But the domain, the closure of the domain is the orthogonal complement of it. So we must have 1. So these are closable relations, and singular relations have been defined as follows. We have 3 equivalent definitions. The main thing is that, in fact, the relation is singular if the closure decomposes into 2 subspaces, in the product of 2 subspaces. And clearly, I hope, it is true that if T double star is this Cartesian product, then this is the same as the domain of T double star as the kernel of T double star, and the range of T double star is the multivalued part of T double star. Because you can see that all these elements act independently in the Cartesian product. So if you see this, then also it is clear that T star is singular if and only if T is singular. Because if you apply the definition of singularity to an adjoint, then you see that if you take the adjoint of this definition, T double star is domain T double star times the range of T double star, you get that the T star is actually the orthogonal complement of the range of T double star times the orthogonal complement of the domain of T double star. And so you're back in the other equivalent statements. What I try to avoid in this talk is any analytic characterizations for regularity or singularity of relations. And the idea of the talk now is that if we see a linear relation, we would like to make it into a sum of regular and singular terms. This will be the main theme. Maybe what I should do is to give an example of a singular operator. Maybe this is well known anyway. We take H is L2 0 infinity. We have also normal basis En, a sequence Xn going to plus infinity, and D denotes a set of all continuous functions with compact support. Then we define an operator by pairs like this, F and then the infinite sum Fxn En, where F has compact support. So clearly the T is a finite sum. And so T is an operator, well-defined operator, and the domain is dense. And now if you take an element HK in the adjoint of T, then you must have the equality in the middle of the page for all F. And now the idea is that you take one index N0 out of this increasing sequence Xn, and you make a neighborhood around this point N0, around Xn0, that is small enough that it does not contain any other points Xi. And then you take Bell functions around it with the support in this interval, such that they are all 1 at this point, and such that the L2 norm goes to 0. Then in fact you see from the definition above that the orthonormal vector E and 0 against H goes to 0 as this sequence R goes to infinity. And that means that H is equal to 0 because H is orthogonal to any element of the orthonormal basis. So H is equal to 0, but then you see from the defining relation that also F inner product K must be 0 for all F in the dense set, so K is equal to 0. So you see that T star consists of 0 cross 0. And so this is a surprising example because you see that this densely defined operator T has a closure that is the product of the sum of the spaces, the product of the spaces here. And by restricting just to finite sums, you can make it a bit simpler. But these things happen when you talk about linear operators. Now, before I start looking at these decompositions, I would like to spend a little time on the complemented sum of operator range spaces of the Branges and Rovnyak, because they will play a role in our decompositions. So if you take a non-negative contraction, then you can in fact provide the range of the square root of A, indicated as above. A square root phi, A square root psi in this new inner product is just the projections of phi and psi onto the orthogonal complement of the kernel. Now take a pair of such non-negative contractions, each with their own operator range space, script x and script y. And then, in fact, you have a non-orthogonal decomposition of the space K as x plus y. But this is not orthogonal, and there is an overlapping space. And in fact, the overlapping space corresponds to the product x square root times y square root. This is a commuting product. And in fact, the inner product on L is given as indicated. And actually, what you see is that the overlapping is 0 if and only if x and y are a pair of orthogonal projections. Together with this decomposition of the space, one can make an operator from K to this product space. As indicated, we just look at a column operator, meaning that we look at H and we add to H the column XY, Y, XH, YH. And then if you think a moment about it, you see that actually V is an isometry in the new inner product. If you look at XY plus Y, XH plus YH, and you remember the definition of the new inner product, you get actually XY, XHH plus YHH, and the sum is the identity. So it is an isometry and the range is closed. But now look at the adjoint of this. So we go back from X cross Y to H, and it is clear that actually the adjoint takes the pair F comma G back to the sum F plus G. And this means actually that the sum F plus G satisfies the indicated inequality. We have a Euclidean Pythagorean inequality. And we know that actually there is equality if and only if F is XY, XH, and G is YH. And in that case, you see that H can serve as F plus G. And now it is interesting to look at the orthogonal complement of the range of V. We are still talking about the orthogonal complement in the product of these script X plus script Y spaces. And so you see that if you just calculate this, the range V orthogonal complement is as indicated. But actually this means that the elements in the orthogonal complement have the form phi minus phi, where phi is in the overlapping space. And so you see that actually the kernel of V star, being the orthogonal complement of the range of V, is 0 if and only if this element phi is 0 for each element in the overlapping space. And so V is surjective if and only if X and Y are orthogonal projections. So this is the treatment of complementation and overlapping that we found in Rovnyak some years ago. When we talk about forms, maybe it is good to mention this already, when we talk about the decomposition of forms, we have to take into account a slightly different complementation and overlapping, but related to this one. Excuse me? Okay, I continue then. Excuse me? Okay, so then here we get the definition. We have linear relation T, and we want to decompose this as T1 plus T2, where T1 and T2 are also linear relations. And we want to have the same domains for these elements, for these operators or relations. And we call it the pseudo-orthogonal sum decomposition if we have in the space K a complemented sum of operator range spaces. And we want the range of T1 in script X and the range of T2 in script Y. And what we want for the sum is that for Fg, we have a decomposition Fg1 and Fg2 in T1 and T2 respectively, with G is G1 and plus G2. In general, we would have an inequality, but it is part of the definition of pseudo-orthogonal sum decomposition that for these elements we have equality. So this is how we do it. And I would like to add that since we look at T is T1 plus T2 as this sum, the multivalued parts sum accordingly. And due to this requirement, this sum is direct. The sum of the multivalued parts is direct. And that means, in fact, that in the sum, G is G1 plus G2, actually G1 and G2 are each uniquely determined by G. There is no freedom anymore. Although we have an overlapping space, as soon as we have a pseudo-orthogonal decomposition, these elements G1 and G2 are fixed. So this is the pseudo-orthogonal sum decomposition. And now we will look at a description of these. How can we find T1 and T2? And the fact is that we can describe them in terms of non-negative contractions in the Hilbert space K. So if K is a non-negative contraction in the space K, and we see that the multivalued part of T decomposes as 1 minus K multivalued part T plus K multivalued part T, and T1 is 1 minus KT and T2 is KT, then we have a pseudo-orthogonal decomposition. And conversely, if we have such a sum, and 1 and 2 are satisfied, then we have a pseudo-orthogonal decomposition. So the funny thing is that as soon as we have this, the Branges-Rovnyak decomposition of the range space, we only have to search for these contractions in this way. And now the usual Lebesgue type decompositions that we are interested in is if T1 in this decomposition is a closable operator and T2 is singular. So now the question is, can we in fact characterize the contractions, the non-negative contractions for which T1 is closable and T2 is singular? And that can be done as follows. We have a linear relation T, and let T be a non-negative contraction. Think of K or 1 minus K. And now it is clear that the range, that R times T is an operator, if and only if the multivalued part of T is in the kernel of R. And in the same way, we can see that RT is closable if and only if we have this indication here. Maybe it is looking worse than it is really, because remember, if RT, this product relation, if this is singular, then by definition, we must have that the domain of RT star must be dense. And if you, in fact, translate this back, you have this characterization. And if RT is closable, it means that the multivalued part of T double star is always part of the kernel. And in the same way, RT is singular if and only if the range of R intersection domain of T star is in the kernel of T star. So we were interested in products 1 minus KT and KT, and 1 minus KT regular or closable, you can read off from these conditions, and in the same way, KT singular, you just read off from these conditions. So the question still is, can we satisfy them at the same time, of course? Another thing that is of interest at this stage is if these components T1 and T2 are mutually singular. If we have orthogonal decompositions, they certainly are not. But now using this overlapping, we have a chance that we have mutual singularity. So that means, in fact, that the relation 1 minus kg, kg, these elements, if G is in the range of T, is singular. And now again, we actually see immediately that if this is the case, then T1 and T2 are mutually singular, if and only if K is an orthogonal projection. And that means that as soon as we have a pseudo-orthogonal decomposition, in the case of non-trivial overlapping, we always have mutual singular behavior of the components. So we've just seen that if in all these contractions K we take orthogonal complements, then we have no mutual singularity. And in particular, if we have K is P being the orthogonal projection onto the multi-valued part of the closure of T, then actually we have an orthogonal decomposition of T. And this is the so-called Lebesgue decomposition of T. And one might ask, what is so special about this one? Well, at least it shows that among all pseudo-orthogonal decompositions of a linear relation T, there is at least one that is not trivial. And how can we, in fact, see that this is uniquely determined? Well, in fact, the regular part, that is 1 minus P acted on T, this regular part of T is maximal. If you take any closable relation below T, then it is below the regular part of T. So the regular part, 1 minus Pt, is unique in this sense. And to more or less close this part of the talk for linear relations, when do we know that the Lebesgue decomposition is the only one among all pseudo-orthogonal decompositions? And actually, the condition that Ando, in his particular situation of a pair of non-negative operators, came up with is true here. T has a unique Lebesgue decomposition, even only if the domain of the adjoint is closed, which is the same as the regular part, the closable part is bounded. Before I go to the next slide, maybe it is good to realize that linear relations come in many forms, and we will be interested in linear relations of the form L phi psi being phi h psi h, where phi and psi are bounded linear operators. And you can easily see that if you take the adjoint of this linear relation, then you get a set of all pairs kh, such that psi star k is phi star h. I'm mentioning this specifically because if you look at the papers by Ando, you will actually come across the domain and the range of this adjoint. In fact, in the papers by Ando and later papers, you will come across this script D and script R phi psi in the right-hand side of the bottom line. And in this context, you see that actually these sets that are defined in the paper by Ando are interpreted as the domain and the range of the corresponding linear relations. Now I would like to say something about the semi-bounded forms. And I will show that somehow this can be reduced to the linear relation case, but not quite. So we write T in script F, or fat F actually, meaning semi-bounded sesquilinear form in Hilbert space. And all the time we denote the lower bound by gamma. And now what we shall make use of is the notion of a representing map for a non-negative form T minus C, where C is below the lower bound. Then Q must be an operator. The domain of Q is the domain of T, and T minus C acting on an element phi psi is Q phi and Q psi, the inner product. And the idea is that for every C below the lower bound, gamma, you have such a representing map. But note that you can choose C, and with different C's, you can have different representing maps. these representing maps can be defined almost uniquely, but I will skip that for a moment. And now the funny thing is that, remember the definitions of closability, closure, and singularity of forms. This is exactly the same thing for the notions, for the corresponding notions in the representing map. So for instance, if T is closable, which is here the usual definition, then Q is closable, and conversely, closed, Q is closed, and T is singular, then Q is singular. Now remember, the representing map is defined by T phi psi is C phi psi plus Q phi Q psi. What can we say about the closure of the form? Well, if T is closable, then we know that Q, the representing map, has a closure, being an operator, and then it would make sense to write down the bottom line. The closure of T is actually the corresponding identity, but now with Q replaced by its closure. This makes sense, and actually it is true. And this is an observation that is really very helpful. Well, first of all, look at a form T with representing map Q. And I will introduce the Lebesgue decomposition of T now. Just look at the representing map Q and decompose it via its own Lebesgue decomposition. So we take the multivalued part of Q, closure, P is the orthogonal projection onto it, and Q regular part is 1 minus PQ, and Q singular part is PQ. And now actually what you see is if you use this decomposition of Q in the regular part and singular part, you get precisely the same thing for the regular part and the singular part of the form. So this is not something very different from what we have seen for the relation case. This actually covers the idea of Simon. And actually you see the same thing happening if you take any Lebesgue type decomposition of Q. We have P as an orthogonal projection, the same thing works. So that means that we should be interested in non-orthogonal decompositions. And actually, this is what we have. T is a semi-bounded form with representing map Q. And now we assume that the range of Q is the whole space. This can always be assumed without any restriction. And then we can say that actually T is T1 plus T2 with equal domains, T1 semi-bounded with lower bound, and T2 non-negative. And actually, this is true if and only if we have a unique non-negative contraction K, such that T1 is 1 minus K square root cube phi, 1 minus K square root cube psi. And T2 is Q square root Q K square root Q psi. So now you see actually that for the contractions that are not orthogonal projections, we have something different. And I will not explain this in detail. Here again, we can say that this business is only of interest if K is non-orthogonal, because if it is orthogonal, we just get the usual decompositions with orthogonal complements back. So the idea is that actually we can look at the decomposition of T in terms of these 1 minus k square root q, 1 minus k square root q on the top line. And so what you see is that this is a different way of using the representing map for the sum. And actually, if we look at T1 and T2, and you remember the definition of a parallel sum, then this parallel sum is a measure for the interaction of the T1 and T2. But now if you connect the T1 and the T2 in terms of this non-negative contraction earlier, then you see that actually the sum decomposition of the form in T1 and T2 via K can be written now via this parallel sum of T1 and T2. And actually this is, now you have a parallel sum of forms, and you see that via this K business, this translates into the parallel sum of 1 minus k and k. And so here you see that actually it is about the representing map 1 minus k square root, k square root. And so the funny thing is that if you look at a form T and the corresponding representing map, then the form is closable. The form T1 is closable if and only 1 minus k square root q is closable, and T2 is singular if and only if k square root q is singular. So these are really different ways of describing either the Lebesgue type decomposition of Q and the Lebesgue type decomposition of the form. You have different conditions. And so it is interesting to note that these conditions are equivalent when K is an orthogonal projection. But in general, you don't have equivalence of these conditions. All you know is that 1 minus k q is closable if and only if 1 minus k square root q is closable. And k square root q is singular if and only if kq is singular. The other ways are not true in general. And in fact, we have an example that shows that the converse statements for the above two implications do not hold simultaneously. I think I will now go to this Ando business because that would fit into the rest. So if we look now at the situation of Ando, then we should remark the following. For A and B Hilbert space operators, which are non-negative operators, we introduce these spaces D square root A square root B and R A square root and B square root as indicated. Then we call B Ando regular with respect to A if this d a square root b square root is dense. And we call b Ando singular with respect to a if d a square root b square root is in the kernel of b square root, or the other way around. And so Ando was interested in the decomposition B is B1 plus B2, where B1 is Ando regular and B2 is Ando singular. And now, to make the connection with what we've seen earlier, we can always write a non-negative B as an operator psi star times psi. And so, in fact, B eta zeta is psi eta psi zeta is just the representing map for B. And in fact, what we can see is that B has a sum decomposition, B is B1 plus B2, non-negative, if and only if for some non-negative contraction K, we have B1 is psi star 1 minus K psi, and B2 is psi star K psi. And actually this is not so difficult to see, because you see that in fact what we can use here is Douglas inequality. And so we get this contraction for free. So in the bounded non-negative operator case, this sum decomposition is rather straightforward. And once we have that, we can write this decomposition again with a new representing map as indicated. And so it is no surprise now that this representing map is minimal, even only if K is an orthogonal projection. So we also use a representing map for A, phi star phi. And then if we do that and we fix phi and psi, once we have A and B fixed, then we can say immediately that B is Ando regular with respect to A, if and only if the linear relation phi psi is regular. And in the same way, B is Ando singular with respect to A, if and only if L phi psi is singular. So you see that our quadratic conditions are now brought back to linear conditions. So you will assume immediately that the following theorem is true. We have a Lebesgue decomposition immediately, because we look at the phi psi and we look at the Lebesgue decomposition of phi psi. And since the orthogonal projection is indeed orthogonal, we can relate it back to the corresponding forms. So then the question is, in fact, if we have this Lebesgue decomposition as it was given by Ando, how does this relate to Ando's definition? Because Ando gave it via parallel sums. In fact, Ando constructed a sequence with the idea that NAB, the parallel sum, is below A, NAB is monotonically increasing, and NAB goes to the regular part of B strongly. So how does this relate to what we have been doing? Just recall that the definition of the parallel sum is at the bottom line. So how to relate this with relations? Well, if you have a relation T from H to K, and P is the orthogonal projection onto the multi-value part of T double star, then actually, if an element FF prime is in T, you can calculate the 1 minus pf prime norm as above. This is just a geometric argument. But now think about Ando. In fact, Ando, if we look at this L phi psi business, we might as well take L square root A B square root. And so if we plug in these data in the formula upstairs, ff prime is in fact A square root eta B square root eta, GG prime analogously, then what you see is in fact, you just get this from this formula, that the regular part of B is given by the supremum at the bottom line. I mean, it takes some calculation, but it is straightforward. And now please keep this in mind. The parallel difference of the parallel sum and A is indicated as above. And you see, this is precisely the thing that we wound up at the bottom line here. And now the beauty of the whole thing is that if we look at this parallel difference, then this can be characterized as a strong limit of a monotonically non-increasing sequence. So this is precisely what was going on in Ando's paper. Maybe in view of the time, I will skip these. And I want to say just a couple of words in closing about radon-Nikodym derivatives. I take T to be a regular linear relation. And I take it in the special form L phi psi. So remember, L phi psi is psi h, phi h, psi h. And actually, since L phi psi is an operator, L phi psi acting on phi h is psi h. This is a triviality. And now the question is, how can we see the plausibility of all this coming into play here? And we do that as follows. We have phi and psi, and we are interested in phi star phi and psi star psi. And so we have these two inequalities upstairs. And that means actually that we have another application of Douglas. We see from these inequalities that we can write phi as an operator C phi acting on the square root of the sum, and psi acting as C psi on the square root of the sum again. So instead of phi psi, now we wound up with C phi and C psi. And now the funny thing is, if you look at the relation between L phi psi and L C phi C psi, which we obtained by Douglas' lemma, then the closure of L phi psi double star is L C phi C psi. So this element in the right-hand side, this linear relation in the right-hand side, is automatically closed. And if it is an operator, then we know that the kernel of C phi is in the kernel of C psi, and conversely. You see that from the definition. And now here is the definition of the radon-Nikodym derivative. In fact, R phi psi, the radon-Nikodym derivative, is nothing but LC phi C psi. And you see from the definition that this is formally equal to the product of the relation C psi and C phi inverse. And now the thing that should be mentioned is that the Rado-Nikodym derivative, as we have defined it here, is the smallest of all closed linear operators C, such that psi is C times phi. So you see that the closability condition plays an essential role in defining the Rado-Nikodym derivative. And moreover, with this in mind, now have one quick look back at the definition of C phi and C psi. And so if you look at this, and you keep in mind what we did in the last page, you can see that C phi and C psi are both Rado-Nikodym derivatives for these two linear relations. It's precisely the same thing. And so this means actually that is L C phi C psi, this Rado-Nikodym derivative, is now is C psi C phi inverse. This is the precise analog of the usual formula from measure theory. We have the Rado-Nikodym derivative of the whole thing, and we write it as a quotient of Rado-Nikodym derivatives of phi and psi each. I would like to say something about the Rado-Nikodym derivative in the Ando case, but it is a bit technical. You see, if we have Rado-Nikodym derivative in the Ando case, we have A is phi star phi and B is psi star psi. So the Rado-Nikodym derivative for the elements phi and psi is as indicated. But now actually in the Ando case, we have products. We have psi star psi. And so we have to take products of the Rado-Nikodym derivative R phi psi star and R phi psi here. Forget about this Q around it. And the only thing that we can do now is to write B as the product of R phi psi square root phi and the adjoint closure. This is a bounded operator, and this is not a bounded operator, but a closed operator, and this is a closed operator. So my only reason to show this slide is to show that in the Ando case it is a bit different because of the product structure, and one has to be a bit more careful there. So I would like to mention the papers that we have written with Sebastian and Safranic. And here is some of our more recent work concerning the complementation and representing maps for this situation. So that was it. Thank you for your attention.